Okay, and our last sample problem here dealing with integrated rate laws, we actually finally have a chemical equation. We started out kind of thinking about a chemical equation here with sample problem 16.5. Again, a decomposition, first order reaction. And then in sample problem 16.6, we looked at molecular scenes. And now in 16.7, we're looking at another chemical equation. So they tell us that cyclopropane is the smallest cyclic hydrocarbon. It's got 60-degree bond angles. Remember, with a carbon that's sp3 hybridized, you'd want to have 109.5 degree angles. And so this, again, is very strained, poor orbital overlap, and that makes for weak bonds. So as a result, this compound is thermally unstable. It rearranges to propene at 1,000 degrees in this first order reaction. Now, I told you a little bit of stuff there that's really not important for anything to understand with this chemical reaction. But again, just some review there of some important things to think about. What's important, though, is we understand that it's a first order reaction. Okay? So they tell us that the rate constant is 9.2 per second. So the first question asks, what's the half-life of the reaction? So this one is pretty straightforward at the beginning. They tell us again it's a first order process. So we know that the half-life is equal to 0.693 over the rate constant. So they give us the rate constant as 9.2 per second. And so the half-life is 0.075 seconds. Remember, when we have something that's in the denominator of the denominator as a unit, that means it goes up here. And units of half-life are always going to have units of time, not inverse time. So this means every 0.075 seconds, half of our cyclopropane will go away. The second problem now again asks us to use the integrated rate law for first order processes and asks a question about time. How long, how much time does it take for the concentration of cyclopropane to reach 1/4 of its initial value? Okay, so remember that for a first order process, the equation that we're going to use is the same that we had for chapter 24, and that's the natural log of how much you start out with over how much you have at a certain time is going to be equal to the rate constant times the time that's passed. And in this problem, we're actually solving for this time. So they actually don't give us values for this, but they do tell us that we want the concentration to reach 1/4 of the initial. Anytime you see the word of, you can think about mathematically it being times. So we want to know what time it's going to take for the concentration at that time to equal 1/4 of times the initial value. So what this does is it allows us to substitute in, rather than having what looks like two variables here, we can have the natural log of what we started out with over 1/4 of what we started out with. So our concentration at time t is going to be 1/4 of what it started out as. And why that's important is it really doesn't matter what we started out with, because that is going to be able to cancel. So really we're going to have the natural log of 4 equals, we know what our rate constant is, 9.2 per second. And time is what we're solving for. We want to know how much time that is. So the natural log of 4 over 9.2 reciprocal seconds is going to be equal to our answer here. And here it's 0.15 seconds. Again, just like we saw up top here, when you have a unit of seconds that's in the denominator of the denominator, the units of your answer will be seconds. So 0.15 seconds. You could have thought of this another way. Remember in our chapter 24 problems, in our in-class problem, we talked about two ways of thinking about figuring out how much time has passed or how much is left after a certain amount of time. We talked about counting half-lives and we talked about calculating half-lives. Calculating half-lives uses this equation to think about how much time will pass to give you a certain ratio. But in this problem, since they tell us we have 1/4 of what we started with, that means that 2 half-lives have passed, right? If we had 1/2 of what we started with, that would be 1 half-life. 1/4 of what we started with, that's 2 half-lives. 1/8 of what we started with would be 3 half-lives. So 2 half-lives passing means we can just take 2 and multiply whatever the half-life is. So 2 times 0.075 seconds, right? We figured out the half-life up here. We can figure out that that's going to be 0.15 seconds. Again, these are two things that we would expect to be internally consistent. So this is the idea of counting half-lives and calculating half-lives. If you know that you have some integer value of your half-lives, you can just count the number of half-lives, again, passing. This equation will always allow you to use any type of a non-integer value for either quantity ratios or time that's passed. That's not a whole number integer of your half-life.